It's my pleasure now to introduce to you one of the 6 most important pioneers in robotics, Professor Lydia Kavraki from Rice.
Thank you, Seth. Thank you. I never imagined I would be standing in front of you today talking about 30 years of research on sampling-based motion planning. So what's the latest? With our most recent developments, we can do online planning in milliseconds on a conventional CPU, fast enough to plan in lockstep with point clouds coming from a depth camera. So full motion planning capabilities in the presence of unmodeled dynamic obstacles. In the future, motion planning is not going to be a limiting factor for having robots in factories, in hospitals, in our homes. How did you get here? It only took 30 years, and I'm going to tell you the story. In 1994, I was at ICRA, and I presented a paper titled Randomized Preprocessing of Configuration Space for Fast Planning. At the time, this work solved problems that were out of reach. Running times, tens of seconds. It was slow. But we need to put this work in context. At the time, in 1987, John Kani amazed us with an algorithm for solving the motion planning problem, the path planning problem, in time that was singly exponential in the number of degrees of freedom of the robot. Several complexity results, high complexity results followed. So it was clear that complete solutions to this problem were impractical, and several algorithms with weaker performance guarantees emerged. Among them, the randomized path planner of Barakand and Latom in 1991 is a landmark because it forced us to consider novel ways of searching the solution space of this problem. In that case, it was random walks on potential fields inspired by the work of Sama Khatib's. And there were many other algorithms, and maybe not surprisingly, with very common elements. In particular, we at Stanford and the group of Mark Overmars at Utrecht arrived to almost the same solution independently. So we decided to collaborate, and the result was the 1996 TRO paper on probabilistic roadmaps. Planning times, tens of seconds. How did we solve this problem? Well, we built on the idea of configuration space of Lozano Perez and Wesley. This is the space of all possible placement configurations of the robot. Every degree of freedom adds a dimension. The robot is a point in that space. We don't know how the obstacles look like. It's too complex to compute them, but we can sample the space. We only need forward kinematics and collision checking. And we can connect neighboring configurations in that space. We only need forward kinematics and collision checking. So it's easy to build a roadmap in this space, and once you have the start and the goal connected to that roadmap, then you have a path for your robot to get from start to goal. We almost obtained an approximation of Kani's algorithm good enough for many problems. The winning idea was sampling. It was simple, but it worked. And this was confirmed concurrently and independently by many people. And today we've ended up with a number of algorithms that are sampling-based motion planners. We call them SBMPs. And their algorithms got better, running times dropped. And good thing, some people worried about the optimality of solutions, because if you apply these algorithms naively, you get terrible paths back. Now, in retrospect, we can say safely that there is no planner that is best for all cases, all metrics. That lazy evaluation, which says don't do the hard work until you really have to do it, is very powerful. And the theoretical analysis of these planners is possible and also insightful. There are trade-offs that are being made. We lose completeness for speed, and these trade-offs were characterized by us and by others. So to help the development of SBMPs, my group developed the de facto source of SBMP implementations, the Open Motion Planning Library. This library, the work on this library started in 2000, and the library was released in 2008. Many people from my group developed this code, but most notably, Mark Mold had a very significant contribution. Now, with over 40 planners and more than 81 contributors, this library is a source for the community. Planning times in seconds. My group exploited the fact that we had fast motion planning algorithms to work on planning with various constraints, to work with planning with uncertainty, partially known environment, multiple robots, a lot of work on task and motion planning, and on having a robot working close to a human. And we also got inspiration and worked on docking techniques for developing therapeutics in biology. So fast forward now 30 years. ICRA 2024. It was a pleasure to work. Two young researchers from my lab, Will Thomason and Zach Kingston, worked to speed up the execution of SBMP planners from seconds to microseconds. How was this done? Well, we exploited a feature of all modern CPUs, which is single instruction, multiple data vector parallelism. Its use unlocks a set of algorithmic improvements in the most basic operations of these planners, forward kinematics and collision checking. And the result is kilohertz planning on a conventional CPU. You can see here an example with a comparison with a baseline. VAMP, the vector accelerated motion planner, plans in microseconds. SBMPs are difficult to parallelize. The reason is that they plan naturally, sequentially. They blend operations that are naturally sequential and naturally parallel. So what happened, and the winning idea, was that we use SIMD at the level of individual operations. That is forward kinematics and collision checking. And the result was planning in microseconds. Here is an example of running RRT Connect on a PC. VAMP is in blue. The y-axis is a time scale. It's a logarithmic time scale. And you can see a clear separation of the performance of this planner compared to the baselines. However, if you look on the right, the lengths of the path that we are finding are almost the same, which means that we are finding very similar paths at much, much faster. And what is more important is that because we use only SIMD parallelism, which can be found in many architectures today, this VAMP planner runs on low power hardware. For example, this Orange Pi here. It runs in milliseconds. So what about environments where we have dynamic changes? It can be done with caution. Here you see the point cloud that we obtained from a ceiling in-depth camera. What we do is that we receive a point cloud, we build a scene representation, and we plan from scratch using a SBMP planner. This is made possible by a novel data structure that we call the collision affording point tree, or CAPT. CAPT allows a collision checking which is SIMD friendly in nanoseconds, which means that we can plan in milliseconds, and we have a plan before the new point cloud arrives. So I'm very optimistic about this result. I think it's time to revisit solutions that we have had in the past about planning with uncertainty and constraints, about planning with complex robots such as humanoids and multiple robot systems. We need to rethink about task and motion planning and also the relationship between planning and learning. It is possible to have hardware solutions for the motion planning problem, I believe, in the future, and in general, accelerate progress to create robots for people. This work has been supported by NSF, and I'm thankful to NSF for that, and OMPL was supported by NSF and originally by Willow Garage. Many thanks to my students over the years, but also to the many users of the OMPL library. And thank you for your attention.
We have time for questions for Professor Kavraki.
It's very hard to see. I cannot see.
Hi, great talk. Thank you so much. I was just curious if you could talk a little bit about this planning versus learning sort of, I don't know, versus maybe is the wrong word, but planning and
Yeah, I wouldn't-
learning and how to think about that as a community.
Yeah, I wouldn't say versus. I would say and. Yes, and. No, the
guess
point
the
I was
role of each.
yes, the point I was trying to make is let's use the right tool for the right task. When it makes sense to plan, let's plan, because planning is becoming really, really fast. It's not the bottleneck anymore as it used to be. I mean, it used to be the bottleneck a few years ago, and we had to take that into account. Now it's getting very, very fast. So how does this change the picture? How can we do planning and learning at the same time for long horizon problems, for really getting to a class of problems where solutions right now are not possible?
Great, thank you. Really interesting.
Thanks. Let's thank Lydia again.